Welcome everyone to this evening's webinar, which is Structural Engineering for High-Rise Precast Buildings. This is going to demonstrate or show an exemplar project, chapters in London, which really demonstrates fantastic collaboration, technology, MMC, innovation, sustainability. It's an award-winning project, and it is presented by one of my old companies, so we're going to welcome them later. Just some housekeeping. You can ask a question at any time via our Q&A feature, which you can see there, and we will be responding to those in the plenary section at the end of the presentation, but you can send questions throughout. There is also a useful resources section within your page, which you can also use to pick up additional resources. Should you have any technical issues, please don't put that in the chat, but just refresh your browser to test the connection using the button, or you can email our events team, events@istruct.org. You can also see speakers' profiles at the bottom of the screen. Just some copyright to go through. To the best of the institution's knowledge, copyright permission has been provided for all materials shown, and this broadcast is therefore presented in good faith. If the copyright holder believes permission has not been forthcoming, then the relevant item will be removed by agreement and appropriate acknowledgement provided to accompany the recording. So now just an introduction to our two speakers, two ex-colleagues of mine. So a very, very warm welcome to Owen Kelly and to Piruz Madaras. Owen is a specialist in precast and modular construction systems with a focus on structural detailing and coordination. And he has played a key role in the delivery of the chapter London Bridge project, ensuring the integration of precast concrete elements with architectural and services requirements. Piruz Madaras, I've known for 25 years. Piruz is a fellow of the institution, with over 25 years experience in delivering complex high-rise and infrastructure projects. He leads Walsh's sustainability efforts and strategic direction on innovative construction methodologies and oversees structural design of several landmark projects in London. Sorry, just going back. So I'm going to hand over now to Owen and to Piruz to present on the chapter's London Bridge project. Thank you, Owen and Piruz.
Thank you, Patrick, for that kind introduction. And fun fact for those that don't know, Patrick actually interviewed me for my first job here and was my boss for a number of years. So it's a real delight to be reconnected in this forum. And welcome everyone, and thank you for joining us. I hope that at the end of this presentation, you walk away shifting what you believe is possible to do, and you take the next steps forward into some of the insights that you take from us into your own projects that you're working on. So what are we going to cover today? This kind of outlines the running order. So I'm going to give a little bit of a background on Walsh, on the system itself before the chapter project, because I think that context is important. Then I'm going to hand over to Owen, who's going to go through the chapter project details and its implementations and some sort of meat and bones of how it's put together. Then he'll pass back to me, which I'll talk a little bit about the sustainability aspects of the project and looking to the future. And then that will open up for questions after that. So hopefully we'll get this done in sort of 30, 40 minutes. A bit of background on Walsh, that for those that don't know us, we are a specialist integrated structural, civil and geotechnical engineers. We are primarily based in London. We have a regional office in Birmingham, and we specialize in multi-story and high-rise buildings that are in brownfield sites and complex site and locations. We work across a number of sectors, but I think we specialize probably in the living sector at the most. And we've been doing this for 35 years. And as Patrick mentioned, I've been with Walsh for 25 years or so. And for those who want to find out more about us, please visit our website or get in touch with Owen and I after this presentation. So the HRS, which stands for High-Rise Solutions, I've got just a couple of slides here to set that context. But before I do, I just want to put a note in there that what you'll see and hear today is what we're communicating as sort of a conduit for the project. We're by no means trying to make this exclusive to us or take credit for everything that's here. We're obviously part of a much bigger team with too many actors to mention. So please take that in that spirit. And now that I've got that disclaimer out of the way, I will continue to try and take credit for lots of things that I didn't do. Right, so I think it's good to start with a project we call NO8, which we got involved with probably around 2015 and 16. So this was a 36-story residential tower in Stratford where Mace were trying to push the boundaries of innovation and find modern methods to build this. And this was kind of the birth of the rising of what was named the Jump Factory. And the premise behind that was basically to prefabricate as much as possible off-site and erect it on-site in a controlled environment. And this rising factory spanned 5 or 6 floors that created an enclosed space to assemble the structure and the construction elements. And I have a little video that I'm going to share in a bit where you'll see that. Then as that project finished, it dovetailed into what we call NO6 or Portland Place. And this was where the evolution step from the Ryzen factory moved to the HRS, which is the high-rise solution. And this solution was actually pioneered in Australia by a company called Hickory that Mace brought over to the UK. And the main difference from that was that the factory was abandoned, if you like, and facade panels were integrated into the floor panels. So what you will see is, in effect, a sequence of construction that was sort of developed iteratively. And I think I am going to play.
Sorry, Peyruz, you're muted.
There we go. Sorry, here we go. So that first bit that you saw was a quick video of the NO8 building, and this goes to NO6. And just so that you can watch full videos on this that are available on YouTube at your leisure. So this video demonstrates some of those sequences that Owen will get in more detail about, but effectively what you have a sequence of floors being dropped in place. You'll see that facade comes in, which is propped on the floor below, with as little in situ elements as possible, which is these were these stitched elements. So the next bit is walls get dropped in. And as you see, this develops, the props go in for the next level, and then you will see columns and would be prefabricated MEP risers that were also went below the slab into elements that were in the core. Then there were utility pods and bathroom pods that had dropped in, which then that sequence was repeated over and over again. So if I pass you over to my colleague, Owen, who's going to take you to the next part of the presentation.
Thanks, Piers. So moving on to what we're all here for, chapter London Bridge. I'm going to try and do a bit of a whistle-stop tour through the whole sequence. To cover the building in detail, I think would be a much longer webinar, but we'll try and hit all the main points and demonstrate how this whole building came together. So what is it? So it's a 40-story PBSA block, and it's above a double basement. And this is located in a very constrained site in central London, directly adjacent to London Bridge Station. So it's worth mentioning some of the key players on this project. Our client, Greystar, the architects, KPF, who did a fantastic job in coordinating with us. Mace is the main contractor. And a special mention to AKT2, who were the engineers on the project and brought the foundations and up to level 5, where the HRS solution then moved forward to the roof. We'll also mention Kelly Formwork, no relation, unfortunately, who were the main contractor in putting this all together. So as I said, it's a very heavily constrained inner city site, and that is a very busy area as well. If anyone knows where this is, it's extremely busy for the entrance into the station and also the roads. With that, we had a max panel width of 2.85 meters that we could bring along these roads, and anything above that was actually a wide load, which meant some quite detailed liaison with the council, and it was quite prohibitive in when you could get these panels and these elements into site. So just taking a look at a bird's eye view of where we are. So you see us there in the middle, Chapter London Bridge. On the right hand side, then you can see London Bridge Station with the Shard directly ahead. And then to the right, you see Tower Bridge, the former City Hall. So as constrained as it can get, very small site, virtually no storage on site. So we had to employ a just-in-time delivery. And to feed this site, Mace actually opened a precast manufacturing facility in Brandon up in Suffolk, and that was on the site of Oranmore's precasting facility. So we'll move to the next slide. Sorry. Thank you, Olga. So how did we implement Mace's high-rise solution on Chapter London Bridge? So this is the typical floor and what's called an asset location plan. So to do this, we took the previous building, which was an RC frame, and we broke this up into a precast frame. So what you can see in the middle there is the slabs, and we had a combination of 13 solid precast slabs and 31 Omnia slabs. And this is a slight departure from the NO6 model that relied solely on solid slabs and stitches between. Then on the right-hand side, you can see our columns and walls. So with that, we had 22 precast columns, 10 precast solid walls, 11 precast twin walls, and alongside that, we had some non-structural precast walls. We had 4 flights of stairs and 2 precast landings. So the main aim of this is to create repetition, create a conveyor belt approach to the whole project. If you can create elements, have them delivered to site and installed quickly and efficiently, that improves your program. And this is the aim of the game with this project. We want to get efficient, quick turnarounds on floor cycles and deliver this project in the quickest and safest way possible as well. So we'll go into safety a little bit more, but the typical slabs, with our slabs at the crown, we actually ended up with over 3,500 pieces of precast, both designed and delivered and installed on site. So this is a view of level 5 where we've started the HRS. As you can see behind there is a core. So the main core in the building was actually slip formed up to level 13, and then we took the precast walls from there. So I'll play a slight video just to show. And this will give you an idea of the amount of coordination and modeling that went in. So to hit the level of detail and efficiency that we wanted, we had to go very deep into the coordination with all of the design team as well as the temporary works engineers. So all this fits together with precise accuracy. So having that level of detail is extremely important to make sure that everything lines up when it gets to site. If something is in the wrong place, if something is not correct, it can be very detrimental to that floor cycle and can stop cycles from going ahead. So I'm going to play a video just to show the level of modeling and detail that we got into. So this is our structural model along with the facade model dropped in. So you can see the very unique facade that was put on this building in the crown. And our technician is very helpfully hovering around. Moving into the actual structure itself, you can see the detail on the floor plates. Now what we'll do is we'll zoom in and we'll go to a specific floor plate just so you can see that. So below this in situ topping, you can see our Omnia panels, which all have the lattice girder used for lifting and also used for stability to modeled. We'll pick some floor plates, some elements, and as you can see on each element, we have modeled each and every cast-in, ranging from the facade cast-ins, the lifting inserts, locator pins, which we'll touch on later. And then looking at a wall, we will take out some walls. You can see we've gone into detail in modeling the well voids, lifting apparatus, lifting cast-ins, and this all feeds into the coordination that's required between ourselves and the rest of the team, construction and design. Then just to pick out the stairs, you can see that we've got full models of the stairs with all cast-ins, ready boxes, which were the invisible connectors. And that just gives you an idea of the detail that is required to deliver a project of this scale. So moving on. The design details and challenges. So kicking off with slabs. Here we have one of our drawings showing a precast solid slab. And if you look at the top left-hand corner, you'll see in the different colors the amount of cast-ins that we had to account for within these slabs. So you've got, for example, a HRS locator. These panels need to be located specifically to where they've been designed for, which we include a HRS locator, which allows the team to locate it on site. We've got cross-prop pins, and they're in for the rake and props, side propping points. So all of this moves into a very high level of detail, very high level of accuracy. To help the precast manufacturers in setting these out, we actually moved into using unique setting out references, which you can see on the bottom. So instead of having just dims without a marking on it, we've highlighted each and every different cast-in and given a setting out dimension for that. That's easy to read. Again, trying to increase that efficiency. On the right-hand side, you can see we had some cast-in plates, and these were to accommodate the crane ties that would need to be installed up the building. So obviously installing these crane ties on a slab that's already been cast halfway up the country is very difficult. So we had to think of a way, how can we bring these in and install those very easily? And that was the cast-in plate details that you can see here. Then you can see our edge stitch around the edge, which is a 450 mil stitch, and this ties the whole floor slab together along with the Omnia panels. This is a typical Omnia panel. So you can see some lattice girders modeled in there. Panels are 70 mil thick, then a 155 mil topping. The lattice is designed both for lifting and then to rest the reinforcement on top of when we're laying the stitch. So again, you're looking to reduce the amount of time in fixing and detailing. And then if you have a look, you can see on the right-hand side, there are chamfered edges. And this is where we use the foam insert to stop grout loss when you infill the topping. And again, the chamfered edges results in you not having a loss of section or loss of cover to the stitching bars that run across. And this is our reinforced concrete topping. So this was installed on every floor. This acts as the tie between all of the panels. Again, there would be additional steel in here to account for crane ties and things like that. And here they are on site. So this is up in Brandon. Here's our panels that have had the facade fixed and they're waiting to be collected. Here's our Omnia panels cast in bulk and stored so they can be transported down to London and then installed on site with our RC topping. Moving on to our columns. So we had a number of different column types on. We had standard traditional dowel connection details, which you can see here. But due to the shape of the floor plate and some very tight corners where we had propping from facade and propping from columns, it became quite difficult to fit everything in. So for these corner columns, we use the Pico column shoes, and they mean that you don't need to prop that column, and it all fits together a little bit easier. You don't have props sitting in the way of everything. So again, thinking of how can we make this all fit together. There's so many moving parts in the building that it takes an incredible amount of coordination with the team and with the pre and during construction. So then looking at our columns. There they are on the left. We have them in Brandon awaiting their trip down to London. And here they are installed with the shard in the background. And you can see, as I said, in the corner of the slab, the amount of props that are at that corner. So trying to add more in there for columns is quite difficult. Moving on then to our walls. So this is one of our solid walls. And again, you can see the detail we've gone to in modeling that. We've got our wavy tails at the top for lifting, our crown foot anchors then for demolding. Again, we've our unique setting out references. Again, working on that efficiency, trying to keep these things moving easily in the shop and have trying to make it easier for everyone involved to try and build. And then we have openings in these for doors, and you can see what we've done here is we put some temporary reinforcement between those, and that stiffens the doors and stops them trying to crack on the way down. So it's just thinking about not just the permanent condition, but also transport and the temporary condition. Here's our walls, and this is our twin walls, which came from Kilsaran, and you can see our ready box connectors on the right hand side pre-installed off-site. Moving on, then we had stairs. So precast stairs, quite common in the industry now, even outside of the precast buildings in the HRS. You can see we've got our ready box connectors, which connect to the wall and provide robustness then as well. And you see our connector plates at the bottom. On the left, you see them being dropped in. So these were critical to get in as quick as possible to enable access to the working deck. So stairs come in, dropped in. And if we move to the next slide, please, Olga. Okay, moving on. The crown. So the crown is a significant architectural feature on the building, and you can see it does stand out. It's quite a beautiful thing. So because it's at the top of the building, getting it built quickly was key. So we had to put a lot of thought in how are we going to get this up and how are we going to increase or reduce that program, get ourselves finished on the critical path. So what was decided on this was to use Pico's delta beam system along with their column system, and then we would provide the internal Omnia slabs. So you can see on the left here, you've got Pico's layout, you've got our Omnias in the middle, and then our walls and the Pico columns on the right. So, and happy enough, this is the tallest Pico delta beam green structure in the world. So it was great today for everyone to go up and see this, but you can see on the right hand side that contrary to the lower levels, we don't have the facade installed in here. And that's because the facade system of this was quite unique, but it had some quite interesting shapes, and the floor slab was also quite an interesting shape, and it had a lot of different lines on it. So Pico were able to install permanent shutters on their beams, which very much helped with keeping the shuttering. Basically, we could bring it in straight off site, clap them in, and then bore with the Omnia slabs. So here's some pictures. We've got our delta beams being fixed. You can see our Omnia panels in between with the fixers on site getting ready. Within the delta beams, you can see the voids to allow for the tying reinforcement between, and that provides that robustness. And I actually have another video to show things going together. So thanks to Mace for providing this, but I just wanted to show this video to give you an idea of the speed of this construction. So you can see that it just becomes a continuous cycle working in the same way. And I think Kelly Formwork did a very good job of taking this and really learning where to get the efficiency out of it. You can see the propping on in the slabs, the bathroom pods are dropped in blue sky. So they can be installed before the next level goes on, which really helps. You can see our Pico delta beam system going through here. So this is the crown as we move towards the top, and you can see the speed of construction on this obviously really just accelerated to get us to the top. I'll stop us here, but everything on this was precast. So you can see our precast BMU plinths, precast plant plinths. So very, very quick construction to get it in just in time delivery. Now, getting to site. How did we get from Brandon to London and from everywhere else? Townfield Precast also and Kilsaran. So, just-in-time delivery is the very, very important word here. And that, as I said previously, it's about the efficiency and getting the right things to site at the right time. So you can see where the Oranmore and the Mace precast facility is located up in Brandon. And we travel all the way down to London to where we install them on site. Now, I will caveat and say this might not be the exact route. So if Neil is on the call, please don't berate me afterwards. But you can see the distance from where we were and where we had to come to. And here is a picture I'm quite happy with. So this was the picture that I took as I was walking to work one day. So if anyone saw a man in a suit running after a truck with his camera out, that was me. But very excited to see our panels and our units start to be delivered to site and start to get installed. So all the hard work that we had put in with the design team, with the Mace team, was starting to come together, and it was a good day to see that rolling past me. So if we change the next slide, please, Olga. Putting the pieces together, so very important part. So obviously with over 3,500 pieces of precast to monitor, to get to site, to install, it's extremely challenging to monitor and track every piece that's going and that's sitting in the yard. So you need help with this. You need a digital twin, and that's where Wynomia came in that they offer a digital twin system. And on the left-hand side, you can see one of their castings, which is linked to each individual piece of precast with their unique reference number. And these are tracked from the moment we release our drawing to having it installed on site. So on the right-hand side, you can see our building, which was an interactive model that we could get a hold of online. And you can see green is installed. We have drawing issued, drawing rejected, which hopefully wasn't too often, but you know, these things happen. And we were basically kept the entire project transparent between the whole design team and the whole construction team. And I think that's a really important point, that the communication between us all there was always open lines of communication. So that's the key to delivering projects like this, is to always be communicating, always be transparent, know exactly where you are, what you need to do. And I think we did quite a good job with the design team and with Mace and the rest of the team on this, that we were all very transparent. We all knew what we needed to do, and there was nowhere to hide at times. So here's actually putting the pieces together. So as I said, the pods were installed blue sky, and that meant a little bit of additional work for ourselves, just to work through concrete curing times and when we could strike, when we could drop pods in, when the concrete got into a point where it was ready to take these loads. And that was helped by the introduction of thermocouplers, or cast-in units into the concrete that monitor in real time the strength. So that's how to the line we went with the design and with the build, in that we were monitoring this concrete after it was poured to find that sweet spot. When can we get these pods on? When can we strike? When can we get on with the next cycle? And that all leads into, again, that efficiency in program and efficiency in the build, and getting those cycles down to the 1 week turnaround. So with that, the Mace actually and Kelly's achieved a 6 floors in 6 weeks turnaround. So it was really, really impressive for pathing pods and facade to be pre-installed. But I haven't mentioned the elephant in the room, and that is adverse weather conditions. So unfortunately, there was a lot of wind, and getting winded off on projects like this can be quite detrimental to the cycles, of course. You've got to stop, and you've got to wait. Basically, you're at the mercy of the weather. And I think it happened a couple of times, but thankfully the team were on board to really push forward and keep going with the build. So here's just a couple of details. On the left-hand side, you see our 450mm stitch, and that is actually between 2 solid panels. So with that, we'll drop in our tying reinforcement, and that'll tie the whole thing together. And in the middle, you can see that where the reinforcement has been fixed, we're all tied together. On the right-hand side, then you'll see one of our wall connections. So this is for the very large solid wall that is to the north of the floor plate. And these get dropped in, the tying steel gets put in there, and they get grouted in. So continuous improvement, and Piers touched on N08 and N06, and obviously chapter is another iteration of the solution, but continuous improvement goes beyond project to project. It needs to happen during the project as well, and that's something that we really pushed on this as well, as from level 5 to the roof. How can we make every floor a little bit better than the last, and how can we continuously challenge ourselves to improve this, improve the solution, improve the build? So with that, we made sure that we were always open, always listening. So we had workshops with site teams, workshops with steel fixers. We took that feedback and we said, you know, what's easier for you guys to fix? That's within the realms of possibility for ourselves. We took that and we looked at each floor slab again going up. So as the contractor improved their cycles, we were looking at improving our output and our cycles as well. So with that, we really attacked the floor slabs, and we managed to get a 12% reduction in the steel tonnage, and that was between level 5 and level 35, which was the last typical slab. And that really does come down to the communication. And I've said it a few times in the presentation, communication is absolutely critical to any of these. To any project, communication is critical. But when you're dealing with, as I said, over 3,500 pieces of precast, if you're not speaking with everyone around you and just open and transparent, this whole thing can fall apart. And it's a testament, I think, to everyone that I mentioned at the start, that the communication was very transparent and very friendly, and everyone was a very tight-knit team, and that led to the success of getting this project delivered. So on that, I'm going to pass back to Piers for a moment, and he's going to bring us through our sustainability bits.
Great, thank you, and that was excellent. So in this bit, this could be our presentation on its own again, but I thought it was important to include a section on sustainability and anticipation of questions. But again, I suppose a little bit of background in terms of how we're measuring sustainability in our context, and we are talking about it in the language of embodied carbon, which is another way of saying sort of energy into the building. And the graph that you're looking at there is the embodied carbon of our projects for over the past 10 years. And what that kind of demonstrates is there is a deviation between projects, if you like. It's not an exact science, but what we have developed internally is a calculator that allows us to do that. And for this specific projects, what you're looking at there is the outputs of the embodied carbon calculations on the frame. For what is on the left is the HRS system, and what's on the right is what, let's say, an in situ system. So on the right would be if you had taken the building and built it in situ, whether in RC or with RC and PT, and to see what the comparison is. So I know it's a little bit small there, but what you can just about see on there is that the other thing worth mentioning as well, this is omitting the foundations from level 5 and the crown. So it's more like for like. This isn't a total embodied carbon for the building. So to allow to give that comparison. So you can see the HRS system is about 205 kg CO2, and if we'd gone the traditional, it's about 187. So you're talking about 9-10% extra embodied carbon that's gone into that. Now, it's also worth mentioning that in these calculations, while this is, and I don't want to get too technical for people who are not familiar with the terminology, but this is A1 to A5, which includes transportation, which is generally about 5% of the overall embodied carbon in that category. We haven't deducted for the saving in transportation and the savings for reduction in wastage. So what you're looking at there is basically, I think, better than 10%, but I think there's still going to be more than 5%. And most of that is born out of additional reinforcement, because if you saw what Owen showed you earlier, when you break a slab up, you need to stitch it back together, and that's less efficient than if you had long reinforcement bars. So you end up with 5-6% additional reinforcement in the slab, which accounts for this additional embodied carbon. If that makes sense.
I think as well, Piers, as we discussed, it's important to mention that there are opportunities within the HRS as well. That, for example, I think the slabs, first, about 60% of the embodied carbons within the slabs. So because you've got your permanent form with the Omnia panels and with the solid slabs, you do have that opportunity to potentially look at going down a sem-free route for the concrete on those slabs, which would dramatically help us in that embodied carbon. So I think it's definitely worth mentioning that we're not at the limit of what we can do. There's certainly plenty of opportunities going forward with this, and that continuous improvement again.
That's a really good point, Owen. Yeah, exactly. I think for those people who don't know what sem-free is, basically we're talking about cement replacement. There's two things that work against you in terms of precast. What determines the amount of cement reduction you can put in the mix is generally in the lifting of that section from the mold. And people generally want to do that in less than a day, or even in 10 hours, 8 to 10 hours. And so that initial pull-out strength of the lifting anchors that you need means that you need early strength, so it limits the amount of cement replacement we can put in. Conversely, for what Owen was mentioning, when you do the Omnia or biscuits or the topping, the general outcome of cement replacement is the strength gain is reduced. But when you have a precast element that has been prefabricated, you don't need to keep the shuttering for any longer, in which case the topping can gain strength in its own speed, which opens the door for more cement replacement. So I think in the next iteration, there will be much more opportunity to take advantage of that. So going to our, I suppose, last slide now was looking into the future, is that, as Owen mentioned, that this continuous improvement piece doesn't end. And we have been looking at the next iterations. This is actually a commercial building, again with Mace, where there is prefabricated element in another form. So I think what I want people to take away is that this is an evolving thing, and you have to, I suppose, learn from other people's projects and trying to bring them into your own context.